Okay, so this is a walkthrough on the second question on part one of the free response test that we're doing. So test two, part one, question two. You're given a table of information for time from 0 to 10 minutes, and then we're given degrees temperature of a pot of tea. So we've got a pot of tea cooling, and obviously it can be anything that's cooling off or heating up, and they've used, actually AP has used different items over the years. So the temperature is modeled by a differentiable function where T is measured in minutes and temperature is measured degrees Celsius. Values of H of T are shown above. So part A, use the data in the table to approximate the rate at which the temperature of the T is changing at time T equals 3.5. Show computations that lead to your answer. So there's a specific reason why they chose 3.5. If you look at the table, that's halfway between 2 and 5. So they're kind of flagging you to look at that specific pair of numbers, and they just want you to compute slope, or they're trying to tie the idea that you have an approximate rate of change or an estimate for our slope based on the only information present. So we'd say, okay, so if I want to compute the rate at which the temperature is changing, I'm going to do rise over run. So 52 minus 60 divided by 5 minus 2, and that's going to be a negative 8 over 3. So we're dropping 8 in 3 seconds, and that's the best we can do in terms of an approximate. So that would be our approximation. This is technically a calculator question because it's question 2. You could certainly put that through as a decimal, and that's fine, but you can do it by hand as well. So we'd have negative 8/3, and that would be degrees Celsius per what would it be, minutes? Yeah, minutes. So degrees Celsius per minute. So that's part A, and that's all there is to it. You get a point for correctly coming up with that expression. Okay, and I should put a +1 right there. In part B, they're saying using the correct units, explain the meaning of 1/10, 0 to 10, H of T dt. That's an average value. So that's the average value of the temperatures added up from 0 to 10. So that is the average temperature, average temp between T equals 0 and T equals 10. So that's the average temperature from T equals 0 to T equals 10. That's worth a point, just stating that you recognize that's an average temperature. Then using a trapezoidal sum with 4 subintervals, estimate this. So 4 subintervals, trapezoidal sum. That means do the left, do the right, divide by 2. So again, trapezoidal with 4 is going to be left edge with 4 plus right edge with 4 divided by 2. So we'll use the data in the table to do that. So let's see. Our left edge estimates, so left of 4, we're going to have our first width is 2, and our left edge is 66. Our second width is 3 from 2 to 5, and we've got a left edge of 60. Our third width is 5 to 9, so that's 4, and we've got a left edge of 52. And then our last one is just a width of 1, and we've got a left edge of 44. So there's my left edge estimate, right edge estimate, same widths, right? So we've got our same width structure. And then we're just going to use the other side. So instead of using 66, I'm going to use 60. Instead of using 60, I'm going to use 52. Instead of using 52, I'm going to use 44. And instead of using 44, I'm going to use 43. So then we need to pop these into a calculator and compute them. So we're going to 2 times 66, 2 times 6, 3 times 60, 4 times 52, 1 times 44. And then we're going to do the same thing with the right edge. Add those up and divide everything by 2. And again, this is a calculator problem, so we have the ability to do that. So we have the ability to add these two up and divide by 2. For time's sake, I'm not going to actually plug or show the plug into the calculator because it is just arithmetic. Okay, and when you add those up, so you add those 2 and you divide by 2. So when you take these two amounts and divide them by 2, you get 529.5. And again, you're welcome to punch that into a calculator and compute it, but that is just adding them up and dividing by 2. And then we need to take into account that we have this 1/10 out front. So this is the estimate for the integral. So that's our integral from 0 to 10, or our estimate for the integral. And we then need to hit it with the 1/10 multiplier, which moves the decimal 1 spot. So we've got 1/10 times 529.5, which would give you 52.95. Doing trapezoidal correct gets you a point, and then coming up with the final solution gets you a point. And let's see, using correct units. Using correct units explain the meaning. So this would be degrees Celsius. It's an average temperature, and I should have said the average temperature maybe in degrees Celsius between 0 and 10. I should be more careful with my wording on that. Letter C, evaluate 0 of 10 h prime of t dt. Using correct units explain the meaning of this expression. So let's see. We need to do 0 to 10 h prime of t. Well, I'm not given any, this is part C. I'm not given anything for h prime of t. So I just need to know that when you have an integral and it hits a derivative, it knocks out the derivative. In other words, when you take and integrate a derivative, you get the function. And then doing integration involves also then plugging in the endpoints. So what that means is h of 10 minus h of 0. So mechanically speaking, derivative, integral knock each other out. You plug in endpoints, h of 10 minus h of 0, that the table gave us. H of 10 is 43, h of 0 is 66. So 43 minus 66, which is going to give us a negative number. And let's see, that would be, what would that be? A negative, boy, arithmetic's always tricky, right? Negative 23 is the gap between those two. So 43 minus 66 is a negative 23, and then we need to use correct units. So our negative 23, let's see, if we take the integral of a derivative, our derivative would be degrees Celsius per minute, and then our dt is in minutes, so times minutes means when you integrate a derivative, you're left with just degrees Celsius. So negative 23 degrees Celsius. And then explain what that means. Well, if you take the area under a derivative, think area under a velocity curve, you get total distance. If our velocity is temperature loss here, or temperature change, then the derivative, or the integral, or the area underneath expressed by the integral, would be the amount of temperature gained, or in this case lost, in that 10-minute span. So what that means is negative 23, the T cools 23 degrees from T equals 0 to T equals 10, or that's the amount of temperature lost in that time span. And on this one, you're going to pick up a point for the negative 23 degrees Celsius, and you're going to pick up a point for the explanation that the T cools or drops in temperature between these two times, or from the start to the finish. And then this last one, I always love, and I know you guys are taking tests and it's different for you, but I always love when the AP puts stuff like this in there. They're trying to like contextualize the problem, and they create just these weird scenarios. So we've got at time t equals 0, biscuits with a temperature of 100 degrees were removed from an oven. The temperature of the biscuits is modeled by this particular function. Using the given models at time t equals 10, how much cooler are the biscuits than the T? I just love it because it's, you have this like weird temperature loss competition going on between the T and the biscuits. So how much cooler are the biscuits than the T at 10 minutes? Well, we know what the T is temperature at 10 minutes. It's 43. So we're going to look to compare to 43 degrees. So we're saying, okay, we're going to start with 100 degrees. That's pretty hot. We then have a rate of change, B prime of T. That's how quickly the temperature is changing. Notice it's negative, meaning it's going downward. And so we're saying we're going to start with 100, and then we're going to account for the loss. And the way you account for loss in this model is we're going to say, okay, let's start with 100 degrees. And then we don't actually know we're going to lose temperature. I mean, we do common sense-wise, but from a equation standpoint, we need to plug that in. So negative 13.84 e to the negative 0.173 t, and then dt. So, I mean, if you didn't know what was happening here, that potentially this could be adding temperature to it. If it was in the oven, if you weren't like common sensing it. So what we need to say is take the starting temperature, add to it whatever the integral is saying, and in this case we're going to get a negative value when we do that, so the temperature is going to decrease, but we need to account for that, or we need to show that that's what we're doing. We're then going to compare this back to that 43 degrees. So we're going to remember 43 degrees is our T, and we're going to compare back to that. So let's see, for this one we definitely need a calculator, and again, this year's exam you're not going to use those, but it'll be a similar, it could be a similar field question to this, just something you would do by hand. So we integrate negative 13.84 e to the negative 0.173. So I'll go to my calculator, and I'm going to go negative 13 point, I already forgot the decimal, 13.84. And then I'm going to go E. Let's see, where's my E? Boom, boom, there's my E. And then it's negative 0.173 T, or in this case, we'll use an X because that's where our calculator is programmed, and then we'll graph that thing. And certainly you can compute the integral in another way. I like to do it off the screen or the graphing screen. And you can see there the derivative line is below the axis, which means we're losing temperature. And we're going to compute, so I'll go second trace or calculate an integral. It's option 7, and we'll do from 0, hit enter, go over to 10, hit enter, and there's all the degrees I'm losing. So I'm losing 65.817 degrees. So I'm going to go back. I'm going to say, okay, that's worth 65.817 degrees. I'm taking that away from 100. I think I can do this in my head. That'd be 34. That'd be 183? 183, yeah. 34.183 degrees Celsius is then what these biscuits are measuring for temperature at 10 minutes. So correctly computing the integral gets you a point, making sure you use the 100 gets you a point, and then doing the comparison, the final kind of nonsense thing. We need to compare back to the 43 degrees and say, okay, well, the tea is warmer or the biscuits are cooler. Let's see how they asked it. How much cooler are the biscuits than the tea? So then your very last point, and this is the little bit I chuckle at, is they're actually having you compute this amount and saying the biscuits are cooler than the tea by whatever the heck that is. So 43 minus 34.183. So I'm going to subtract those out. And what is that going to be? 8.817 degrees Celsius. So the biscuits, we'll write it out. The biscuits, that's a tricky word to spell. Biscuits are 8.817 degrees cooler than tea at t equals 10, or at 10 minutes. Good times, fun little fun fact at the end on your biscuit versus tea temperature loss Olympics. So that's it. Those are the 9 points on this one. It's a good question. It's varied. Has a lot of nice little pieces in it in terms of how maybe they'll ask a multi-part question this year sort of deal. So that's it. That's the solution. And the other two you can check on the solution sheet.